In today's video, we're going to be talking about L'Hopital's rule, which is a rule we can use with limits in order to find limits that are in an indeterminate form. As we do these example problems, I'll point out what some of these indeterminate forms are so that way you know what they are and when to look for them. So first of all, let's define what this rule is and why we use it. If we have a function of x approaching c of one function being divided by another function, and that limit ends up being an indeterminate form, then we can use L'Hopital's rule in order to figure out what the limit of this function is. In order to use L'Hopital's rule, all we have to do is change this problem to the limit as x approaches c of f prime of x divided by g prime of x. In other words, the derivative of the top function and the derivative of the bottom function, and this will give us our new limit. Now sometimes you have to do this multiple times, so you may have to take the second derivative or the third derivative in order to find the limit. And we'll talk about that in a minute here when we do some example problems. A couple common indeterminate forms include infinity divided by infinity. We have an infinitely large number being divided by an infinitely large number, and we don't really know what that equals. Another common one is 0 divided by 0. We have 0, which is nothing, being divided into 0 groups, and we don't know if that equals 0, if that equals 1, if that equals infinity. We don't know. These are the two most common ones, but we'll also talk about a couple other ones as we get to them throughout this video. Let's do our first example problem. In this example, we want to find the limit as x approaches infinity of natural log of x divided by the cube root of x. Now, let's try solving a limit like we usually would, by plugging in whatever x is approaching into our function to see if we can find a limit. If we were to plug this into our function, we would get the natural log of infinity divided by the cube root. By the way, this is cube root. I know that 3 is a little bit hard to read, but this is the cube root of infinity. And this is equal to infinity divided by infinity. And this is one of our indeterminate forms that we don't know what that equals, so we're going to have to use L'Hopital's rule in order to figure out what this equals. As we discussed a minute ago, to use L'Hopital's rule, all we have to do is take the derivative of the top function and the derivative of the bottom function, and then plug in whatever x is approaching again to find our new limit. So let's do that. So let's change this into the limit as x approaches infinity. We don't change what x is approaching, we don't change the fact that we're finding the limit, we just take the derivative of the top and bottom. The derivative of the natural log of x is 1 divided by x. And the derivative of the cube root of x, well, remember, the cube root of x can also be written as x to the 1/3 power. And since this is a power, we can use the power rule to find the derivative of this function. So this would be equal to, first we need to bring our power to the front, 1/3 times x, and then we need to subtract 1 from 1/3. 1/3 minus 1 is equal to negative 2/3. So this is our function on the bottom. 1/3 x to the negative 2/3 power. So now we're in a form where we could actually just plug in infinity and find our limit. This would equal 1 divided by infinity divided by 1/3 times infinity to the negative 2/3 power. 1 divided by an infinitely large number is 0, so this is equal to 0 on top, and on bottom we have 1/3 times infinity to the negative 3rd power, which is equal to infinity. And you might think that this is an indeterminate form, but since we have a finite number being divided by an infinitely large number, this limit is just equal to 0. And that's our limit. As you can see, we just took the derivative of the top and bottom, plugged in infinity whenever we got that, and now we found our limit. Not hard at all. Let's do a couple more examples, and some of these may use a little bit more algebra, so stick with me here. In this example, we want to find the limit as x approaches 0 of x minus sine of x divided by x cubed. Let's plug in 0 and just see what happens. First of all, we just have to replace every x with 0. Obviously, just replacing the x with 0 gives us 0 minus sine of 0 divided by 0 cubed. Now, in our numerator, we have 0 minus sine of 0. If you know your unit circle, you'll know that sine of 0 is equal to 0. And 0 cubed is just 0. So we have ended up into one of our common indeterminate forms. Let's use L'Hopital's rule in order to figure out what this limit is. So now we just have the limit as x approaches 0, and taking our derivative of the top function, the derivative of x is just 1, and the derivative of negative sine of x is just negative cosine of x. Now the derivative of x cubed, using the power rule, we bring this 3 to the front and then subtract 1, so we get 3x squared. Let's plug in 0 again and see what happens. This turns into 1 minus cosine of 0 divided by 3 times 0 squared. Obviously in the denominator, we're going to get 3 times 0 squared, which is 0, which could be a problem. But then we have 1 minus cosine of 0, which is 1 minus 1. This is a 1, sorry, which is just equal to 0 divided by 0. So what do we do in this situation? Well, we just have to take the derivative again. So let's take the second derivative of our function. In other words, the derivative of this function here. And then take the limit again, and we should be able to find our derivative. All right, let's do it. We have the limit as x approaches 0 of the derivative of 1 minus cosine of x. The derivative of a constant is just 0. The derivative of negative cosine of x, whenever we take the derivative of cosine of x, this ends up equaling negative sine of x, but since we are subtracting this cosine, it ends up equaling positive sine of x. So this is just sine of x on top. And then the derivative of 3x squared, once again, we just use the power rule, so we bring that 2 to the front and subtract 1. We get 3 times 2, which is 6, times x to the first power, but since it's to the first power, we don't need to write it since it doesn't change anything. Now you may be looking at this and thinking, hey, if we plug in 0, we're going to get 0 divided by 0 again. And you would be right, but we can simplify down this limit just a little bit. With limits just like derivatives or integrals, which we haven't gotten to yet in this series, but we'll get there soon, you can pull constants out to the front. And this 6 on bottom is basically just like a 1/6. If you were to multiply the top sine of x and the x times 1/6, you would get this function. So we can pull this 6 out as a 1/6 to the front. So this is now equal to the this is now equal to 1/6 times the limit as x approaches 0 of sine of x divided by x. Let's use L'Hopital's rule here because once again, if we were to plug in 0 here and 0 here, we would get 0 divided by 0. So this then turns into 1/6 times the, times the limit as x approaches 0 of cosine of x divided by 1. And if we were to plug in x equals 0 to cosine of x, we would get 1. So then this just ends up equaling 1/6, and our limit here of x as x approaches 0 of cosine x divided by 1 is cosine of 0, which is 1 divided by 1, which is just 0. So this ends up being 1/6 times 1, which is just 1/6. And that's our limit. Not too bad, right? I know this is kind of a long process, but usually it doesn't take more than 2 derivatives. Sometimes it does, but usually not, so don't worry about it too much. In this problem, we want to find the limit as x approaches 0 of 1 minus cosine of x divided by secant x. Once again, let's just plug in this 0 into our function and see what happens. If we were to plug this 0 into our function, we would get the limit, or sorry, not the limit. Whenever we plug it in, you don't have to write limit anymore because you're taking that limit. So this is actually just equal to 1 minus cosine of 0 divided by secant of 0. Now, cosine of 0 is just equal to 1, so 1 minus 1 is equal to 0. But what is secant of 0? Well, if you know your unit circle, you know that secant of 0 is equal to 1 divided by cosine of 0, which is just equal to 1. So we get 0 divided by 1, which is just equal to 0. And in fact, we didn't have to use L'Hopital's rule at all. That's just the limit. 0 divided by any number not named 0 is not an indeterminate form. It's just equal to 0. This example is just to show that you shouldn't go willy-nilly with your derivatives without checking to see if you're actually in an indeterminate form. So that's going to be our easiest example of the day. Let's continue. Well, one thing I want to mention is since we have one part of the function being subtracted by another part, we can split this limit into 2 parts. We end up getting the limit as x approaches pi over 2 of secant x minus the limit as x approaches pi over 2 of tangent x. Of course, if we plug in our pi over 2 into both of these, we'll end up getting an indeterminate form. This is equal to infinity minus infinity. And the reason it's an indeterminate form is a lot easier to see if we draw the graph. So let's draw a graph here. This graph kind of looks something like this. Here's a parabola, and we have this line coming down, and we have this kind of S-shaped line going up like that. But here, at pi divided by 2 on our x-axis, we have an asymptote. So what does this limit equal? We don't know, but we can figure it out using L'Hopital's rule. Something I do want to mention though, and you may have asked it yourself, you may have noticed that L'Hopital's rule specifically states that if we have f of x divided by g of x, in other words, a function divided by another function, we can use L'Hopital's rule. And this is not in a fractional form. So how can we get this into fractional form and use L'Hopital's rule? That's a great question, and I'm going to walk you through it. So let's do that now. The easiest way to get this into fractional form is to change this into its sine and cosine versions. Remember, secant of x is equal to 1 divided by cosine of x, and tangent of x is equal to sine of x divided by cosine of x. So we can combine those fractions since they have the same denominator. Let's write it out so you have an idea what this looks like. So this will now turn into the limit as x approaches pi over 2 of 1 over cosine of x minus sine of x divided by cosine of x. Now let's combine these since they have the same denominator. This now turns into the limit as x approaches pi over 2 of 1 minus sine of x divided by cosine of x. Now, if you don't have a way to graph your function, this would actually be a great way to show that this function is currently in an indeterminate form. If we were to plug in pi over 2, we would get 1 minus sine of pi over 2 divided by cosine of pi over 2. 1 minus sine of pi over 2, sine of pi over 2 is equal to 1, so this ends up equaling 0 on top, and then cosine of pi over 2 is 0. So we end up getting the indeterminate form 0 divided by 0. In case you don't have a graph, this is how you could show this is indeterminate form and that you need to use L'Hopital's rule. So let's use L'Hopital's rule. We just need to take the derivative of this function, or more specifically this function, since we can combine those denominators. Doing that, we now have the limit as x approaches pi over 2 of negative cosine of x. Remember, the derivative of sine of x is cosine of x, but since we're subtracting, it'll be negative. We have to tack on that negative. And the derivative of a constant such as 1 is always 0. And the derivative of cosine of x is negative sine of x. So let's try plugging this one in. If we were to plug in pi over 2, we would get negative cosine of pi over 2 divided by negative sine of pi over 2. Oh, and I do want to mention that since this is a negative divided by a negative, these negatives will actually cancel out. And this will end up equaling positive cosine and positive sine. This ends up equaling cosine of pi over 2, as we discussed earlier, is 0, and sine of pi over 2 is 1. We talked about how 1 minus sine of pi over 2 is 0, so sine must equal 1. And 0 over 1 is just equal to 0. So our limit as x approaches pi over 2 of secant x minus tangent x is 0. That's the limit. So yeah, this one had a little bit more algebra knowledge and even some trigonometry knowledge, but once you get that down, the rule itself is actually pretty easy. In our last example for this video, we have the limit as x approaches infinity of x to the 1 divided by x power. Let's plug in infinity and see what happens. Well, this ends up turning into infinity to the 1 divided by infinity power. And remember, a finite number divided by an infinitely large number is basically 0. So this turns into infinity to the 0th power. And once again, this is actually one of our indeterminate forms. We have an infinitely large number being taken to the 0th power. But does this equal 1? Does this equal infinity? We don't know. So once again, this limit is currently in an indeterminate form. So we can use some algebra manipulation in order to figure out what this limit is equal to in the first place. We're going to set this limit equal to y. And once again, since we have this exponent here, we're going to take the natural log of both sides. I don't have a ton of room here, but natural log of both sides. Let's grab the green marker and continue. This is now equal to the limit as x approaches infinity of the natural log of x to the 1 over x power is equal to natural log of y. And just like last time, we can take our exponent to the front. This is one of those algebraic rules that you gotta know. It's super helpful to know this one because it can get you out of pickles like this. So then this limit is now equal to the limit as x approaches infinity of 1 divided by x times natural log of x, which is equal to the natural log of y. So now that we're here, may as well try plugging in infinity and seeing what happens here. If we were to plug in infinity for this limit, we would get 1 divided by infinity times natural log of infinity. And then we run into a problem. This ends up being 0 times an infinitely large number, which once again is another indeterminate form. This one, once again, not super common, but what is 0 times infinity? What is an infinitely large number times 0? Is it 0? Is it infinity? We don't know. Once again, this is another indeterminate form. So let's use some L'Hopital's rule in order to solve this problem. After all, this is almost in a fractional form that we can use. We just need to change it algebraically. So I'm going to erase this right here, and we're going to talk about how we can use L'Hopital's rule on this problem. Remember, this limit, or I should say the limit as x approaches infinity, natural log of x times 1 over x is equivalent to natural log of x divided by x. And remember, this is still equal to natural log of y. So now that we're in a fractional form, we can use L'Hopital's rule. So let's take the derivative of the top and bottom function. Let's do that over here. We're going to move up a little bit. I apologize for my organization skills, but we're going to go here and then go up here. So this is still equal to the limit as x approaches infinity. The derivative of natural log is 1 divided by x, and the derivative of x is just 1. Remember, this is still equal to natural log of y. Now, 1 divided by x divided by 1 is still just 1 divided by x. So I'm going to rewrite this as the limit of 1 divided by x. If we plug in infinity here, which we can do now, we would get 1 divided by infinity, which is equal to 0. Remember, a finite number divided by an infinitely large number is basically 0. And this is still equal to the natural log of y. But when does the natural log of y equal 0? That's right, when the natural log is equal to 1. So y is equal to 1. Or I should probably rephrase that. Whenever we take the natural log of 1, the natural log will equal 0. Our limit is just 1 using these natural log rules and a little bit of L'Hopital down here. How about that? But that's the last example for this video, and I hope it helps you out. If it did help you, consider subscribing and check out my other Calculus 1 lessons if you want to learn more. There's a whole giant playlist that I have linked right here. You should totally check it out if you need more Calculus 1 help. I'll see you guys in the next video.